Thank you for the introduction, Chris, and thank you for the invitation to give a talk. And Dr. Bogdan, Dr. Podgórski, and others who organize those talks. I think it's a great kind of way of presenting our research in this tough times. Just to make sure before I start, are my slides visible?
Yes, they are.
Okay, great. So, since I don't know actually even where I am, I said this talk takes place in a Zoom universe, or maybe I shouldn't put a comma there. It's kind of somewhere in the Zoom universe. So the first part of the talk today, will be about wearable devices, and I'll define what I mean by that, and then I will present a few approaches that my group and I were working on. And this is something I'll say a bit about the history, how I got involved in this kind of research area. And it is something that, especially for maybe the students on the listening to this talk, that might give you some ideas of how to start collaborations. Okay. So I will briefly go over what the wearable and the implantable devices are, and then what kind of data they generate. And then I'll talk about the research that my group is doing on so-called micro-scale analysis. And I will concentrate on two aspects in this micro-scale analysis. This will be detection and analysis of walking, human walking, and kind of gait features that we can extract from such analysis. The second part, and I try to make differences in font here, it will be macro scale analysis. That's bigger font. This is not something that I primarily do, but I want to advertise a bit of work of my either former students, postdocs, and my collaborators. So just to, again, more on an advertising side, very recently, last year, we published this article in Statistics in Biosciences called Accelerometry Data in Health Research, Challenges and Opportunities. I think it's a nice overview article, and I wasn't the primary author on this article, but I just want to, so what I highlighted in yellow are either my former visiting scholars, Marta Karash, who is now a PhD student in biostatistics at Johns Hopkins, Marcin Strączkiewicz, he was my postdoc. He's now at Harvard School of Public Health. And Jacek Urbanek, actually, that's how I started working on this data. This was during my sabbatical now about 7 years ago at Johns Hopkins. Jacek joined me again as a visiting scholar / postdoc. We started working on this data. Jacek is now an assistant professor at Johns Hopkins. So what are those creatures, the kind of the wearable and implantable devices? Well, they are, so we call them smart electronic devices. So they have microcontrollers in them, and they can be worn either on the body. Let's say I'm wearing my Apple Watch on my wrist, or they can be implanted. So this technology started gaining popularity maybe over the past decade, and it's one of the things. It's fun to wear such devices, but also we are starting to use them in health research pretty extensively. So some of those devices you might have seen, some of them you probably haven't seen. So this is an kind of early version of Apple Watch. Actually, this device in the middle here, this is the most popular research grade device. And we use them in many studies. I ran a study where we used this in an experiment of, again, walking, driving, and some other activities. So many of those devices, they are more kind of popular devices or pop devices. So all of those in the bottom row, they are worn by, like Fitbit. It's for example, very popular here. The devices in the top row, they are more research grade devices. So they are used mostly to collect the data, not really to provide feedback to to people who wear them. So these were wearable. What about implantable devices? Well, this device, for example, this device here, this is actually implanted. It measures blood glucose level. So it's very useful in the studies of patients with diabetes, let's say. This device, Zeopatch, is actually glued to the chest, and it provides, besides accelerometry measures, it provides also kind of EKG measurements. So this is great. We have the devices, but we are kind of statisticians, biostatisticians, data scientists, so we would like to extract information from the data that are collected on those devices. However, there are some major challenges. So first, data size. And just to tell you my first story with this data, the first data set that actually I was working with, this was already over 6 years ago. I was told, okay, we have the data. Can you get it? You know, and I was like, okay, I will get the data. As it turned out, the data size was half a terabyte, 500 gigabytes. Again, even my laptop, you know, didn't have enough space on its hard drive to store all this data. So I had to go and buy an external hard drive to even get the data. I'm not talking about processing, not talking about the analysis. Another challenge is that this data are very complex. And as I'll show you in a few examples, they're also heterogeneous. So it's very hard to employ kind of more classical statistical techniques to analyze such data. The last point, the last bullet point, has to do more with curation of the data and kind of making use of the data where we hope not to get biased results at the end of the day. So one of the things, and this is more probably to students, but also to researchers here on the call, with such an area, actually there is a need for collaboration between many different groups of people. So it's not enough to just get the data and extract something from the data, because we would like to extract useful information, we would like it actually to be meaningful information that can help in health research. This is kind of my primary area. I'm a biostatistician, so it's something I clearly care about. So let me show you a few examples of the data, and then I'll maybe stop for a minute to see if there were any questions. So this device, this is actually the first device I got the data from, and I collected this data on myself. So this device is called GenieActive. It's pretty popular in research. And when we get this data, this is data, those accelerometers I called triaxial accelerometers. So we get data from each axis or from each channel, usually at the frequency of, it's for sure above 10 hertz, but it's usually the frequency is anywhere between 30 and 100 hertz. So in this data, for example, we collected the data at the frequency of 50 hertz. This is throughout the day, so throughout 24 hours. You can see it's pretty much, we cannot really see, I mean, it's very hard to see what's happening with the data, in the data. Maybe one period, maybe sleep period can be seen, but otherwise it's very hard to see. And again, I'll be mentioning that later, but the question here is it a sleep period or is it a non-wear? So somebody got the device off their hand, their wrist, and just put it, aside. So we might have no data here. The next one, I just zoomed in for an hour of data. Well, it's still very hard to see what's happening here. Only when we kind of zoom in maybe into a minute or even few second interval, we can kind of see what's happening with this data. So kind of more of a visual representation. Now, if you think about it, if we had to go through each minute of the data throughout the day, sometimes throughout the 7-day experiments, well, there's not enough time in the world and not enough undergrads to do it for us. So it would be good to actually maybe develop some methods to analyze such data. One of the ways that people do analyze such data is they take the data from the bottom kind of figure here, and they summarize that as something called an activity count. So we might have an activity count of 2020, but here we're summarizing, in a sense, 9,000 collected numbers into this kind of one number. So as you can imagine, we lose a lot of information via such summary. So before I go to kind of macro and micro scale analysis, any questions so far?
Okay, so I'm mediating this. We are learning here how to initiate a discussion. So as I said, either through chat or directly raising hands by participants. So let's allow this to happen. I just don't see any activity on this site. So probably we will continue. Yes.
Okay, so let me continue. So I showed you a sample of the data, and this was from a one-day collection on the previous slide. So how kind of approaches, more kind of statistical or machine learning approaches to this data are this more common or more popular approach, this macro scale. So for example, here we're summarizing the data for every minute, and then we have so-called activity counts here, and then they will be used in the further analysis. What I concentrated mostly on is this analysis at micro scale. So sometimes we call it raw accelerometry data. And as I said, this data are collected usually at the frequency 10 hertz, 20, and above, usually up to 100 hertz. So what we have concentrated on was, well, seemingly simple kind of goal of detection of walking. However, it took us a few years to actually come up with an algorithm that would be useful in a, as we call it, in the wild, or for the observations done when individuals wear those devices at home, at work, and we give them for a few days, for a week, for 2 weeks. Then we kind of extended this research to detect driving, climbing stairs, resting. We try to differentiate sedentary versus upright activity. So I won't talk about everything that we have done. I'm happy to provide links to the articles, to the manuscripts that we have, but let me summarize a few of the things that we've done. Now, before I do that, why did we concentrate on walking? Well, if you think about it, this is the most common form of physical activity. Again, we study a lot of people who are older, let's say 65 plus, or who suffered from different conditions. So they are diseased populations. So again, it's not the activity that we might have been doing in a younger age, running, playing sports, and so on, but walking is, again, their primary activity. Also, in the past, features extracted from walking were associated with, for example, survival, or with mild cognitive impairment, which is an early stage of Alzheimer's disease, stroke, and other conditions. Kind of we use some data extracted, or we use some features extracted from walking data, and we associated them with different measures of fitness, fatigability, mobility, and so on. This is an article here that we published a few years back. Now, let me tell you a bit more about the data before I go into the methods. So for example, here I'm showing data for 2 individuals, and this is actually from a study that I ran with my PhD student. So even for the same activity, let's say walking, the signal maybe looks similar, but it would be very hard to combine this data at the raw signal level. So in a sense, we need to either extract features or think about smart ways of combining this data. So here, again, this is additional data from a study that we ran. So here we collected data when somebody was walking on the level ground. And here what you see in gray, this is actually a nice thing that, we cannot claim that we came up with that, but we used in our study where this was clapping that generates a lot of acceleration, a lot of changes in the acceleration. But for us, it was a very nice timestamp within the data set where we could differentiate, so for example, this was walking on the flat ground. We made participants walk actually down the stairs, upstairs, and down the stairs again. So we have this nice kind of inside or internal markers that are very useful for further analysis of the data or developing of the algorithms. So one of the things, and this is more recent thing, that actually I cannot claim that this was, that I was primary driver of this work, but this was done on the data that we have collected, and we did it again with, see here, the usual suspects will appear a few times in this talk. This is Marta Karasz, Marcin Strączkiewicz, and Jacek Urbano, who was leading this research. In this analysis, we kind of concentrated on extracting the walking signal and then characterizing the gait, as you can see here in the bottom picture, and also characterizing this gait. So the most common thing is gait speed, but there's also stride-to-stride variability and kind of defining subject-specific gait pattern. So I saw there was a question, so after this slide, I will go to the chat to answer this question. But basically what was done here, we used short time window methods to characterize gait here. And we use those gait characteristics again to associate the gait characteristics with health outcomes. Now, so this was something that was explored in two articles we had published in the past few years, but probably the first article, even though it wasn't the first to be published, was this prediction of sustained harmonic walking. And we published that just a few years ago, but we worked on that for a few years. Finally, we got to publish in Physiological Measurement, but this was really the first article where we used short-time Fourier transform to detect walking. So let me go see the question. Okay. So it was actually a question about asking questions. So
this was actually my attempt to see how it will work, and I had a question, but I wanted to check if you will react to that. Okay. So indeed it works. So to encourage everyone to use this. But my question is that I had is definitely in signal processing, detecting certain events in this type of data probably was quite extensively studied in the past. And my question was how much of this previous research can be utilized here, or it is entirely new kind of things?
So yes, it's a very good question, because of course we didn't come up with short-time Fourier transform. We were not the first to analyze data from signals. The problem here is a lot of research in signal processing assumes some kind of time series properties, be it stationarity, be it, other kind of nice mathematical properties. There were people trying to approach it from maybe functional data analytic point of view as well. The problem here is that these are human data. With human data, especially with the devices worn on the wrist, there is so much, I don't even want to call it noise. It's properties of the data don't fall into kind of nice algorithms that were developed for signal processing. So not to make this answer too long, but actually Jacek Urbanek, he started his career in engineering. And at first, when he started working on that, he said, okay, this will be very simple, because he had a lot of experience with signals coming from machinery, for example, wind turbines. And when he started analyzing this data, quickly he realized that methodology that he knows well and he applied very easily in kind of more machine-generated signals is basically useless here. Well, maybe that's too strong of a word, but the assumptions made in such analysis are, are very frequently not applicable in this human data. We can discuss it a bit more later, but I hope I answered, or at least I gave a bit of an explanation of this data. So let me show you some of the kind of results. I know I haven't talked much about the methods, but it's more of I want to give you a general picture, and then if there are questions about the methods, I can send a few articles to be posted on the website. So in this data, so this was actually the first study. This was this 0.5 terabyte kind of data study where we had data for about 50 individuals. And we had data collected from actually 4 devices. So 3 devices were placed. So there were this Actigraph GT3 X Plus. I showed you one that was glued to the thigh. And the data from this device that was glued to the thigh actually treated as a silver standard to develop the methods. So one of the things here that we did, this is not walking. Here we are trying to distinguish between sitting or lying periods from standing periods. And our goal was to come up with a simple algorithm that will do that based on the meaningful features that are extracted from the data. So when we say meaningful features, there are machine learning approaches, or even going deeper, like deep learning approaches that extract tens or hundreds of features from the data, and then they build classifier, which is basically a black box classifier, and we get this classification at the end. For us, we had this different goal: extract as few features as possible that are meaningful and build a classifier based on them. So the features that we extracted, there were just 2 features. It was median acceleration and then median standard deviation of the acceleration within short time windows. And here, even from this picture, this is data for about 9 individuals. Well, it is data from 9 individuals. You can see that the blood dots and red dots kind of cluster in 2 different areas. So we built a classifier based on the generalized linear mixed models. So basically logistic regression applied to correlated data. And let me just show you the results here in the picture. So we classified the standing and kind of sitting periods, which are much better, much closer to the silver standard defined by the algorithm associated with this active pole. Okay, so we compared it with something that's the most popular method in the literature, sedentary sphere. Okay, so in terms of microscale, what are we trying to do with this data? Well, one of the big goals that we have is this objective quantification of physical activity. So this is something that I hope it's both my group and kind of our collaborators, we've made some progress in that. But it's not only that. it's also, say, wouldn't that be great if you had your Fitbit and the data extracted from the Fitbit would tell you about maybe declining health or kind of recovery of individuals after heart surgery or something like that. So what we have concentrated on, again, from our statistical point of view, was algorithm development and kind of applying or extending statistical learning methods to deal with such data. See, I have another question. Yes, so it's about the choice of the features. Yes, what we have done, it was a subjective choice, but we tried to make it in a meaningful way. So we looked at other features, and in some other research also we extracted features, for example, from the Fourier, short-time Fourier spectra, but this was more applicable to walking data or to periodic activity. So for the feature, we wanted to, so let me explain maybe on this plot. We looked at a few features. However, if you think about standing or sedentary activity, usually the acceleration is not changing much. So here, these are these red dots that the variation of this acceleration is usually not much. Also, usually our hand is placed in a horizontal way. Of course, there are deviations from that, but from those two observations, we said, okay, what kind of feature should we extract to correspond to those two observations or to the intuition? So we decided on those two features. Okay, I won't say much about that. I know I'm running already short on time, but in this macro scale analysis, usually the thing is done in about, well, usually 1 minute intervals. Sometimes there are 15-second intervals. Sometimes there are even longer intervals. So this is actually a study that a former postdoc, Jacek Urbanek, she did a lot of work on. It's a large study of this is a representative sample of individuals in US. It's called NHANES, National Health and Nutrition Examination Survey. And here the data have been collected on over 10,000 people. They have each 7 consecutive days of observations. And here is an example of data from one such individual over 7 days. Again, these are 1-minute summaries. So the big thing that they have done, they developed this data processing pipeline. So actually here, the majority of the work is actually in preparing or in curating the data before actually statistical analysis can happen. There's a package in R actually doing that, and they did actually very nice work. They applied this work. It's not only to NHANES now, they applied it to data from UK Biobank. So let me just finish this part by acknowledging my collaborators. Work that I haven't presented, we recently got it accepted in Statistics in Medicine. It's by Dr. Kos, who is at the University of Wrocław. My collaborators from Johns Hopkins, Jacek Urbanek, Marta Karaś, Ciprian Kranicianu, Vadim Zipunikov, my former student, Billy Fidel at Indiana, Marcin, who is now at Harvard, and the my first collaborator on this data, Nancy Glynn from University of Pittsburgh. So thank you.